Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 26, and in this lecture we are going to discuss a very interesting concept of shear center. So, in the last class we found out how does shear stress vary in the cross section. So, let us think we have a arbitrary cross section and suppose that it is thin and open. We thought of an arc length running from one end of the cross section to the other end, and then at arc length S we had this line and shear stress was assumed to be constant on this line and along the periphery. So, this was tau x s, which is a function of x, that is where exactly is this cross section and the arc length S. It does not depend on the thickness coordinate, okay. And we had found out the formula was as follows. So, this is minus 1 by thickness T s. So, thickness at arc length S, which is this quantity right here T s. So, minus 1 by T s into I y z whole square minus I y y into I z z, then this is multiplied by minus V y, which is a function of x, the axial coordinate x, into I y y times q y, which is the function of the arc length S, minus I y z times q z of S, okay, and plus V z into I y z into q y minus I z z into q z. Okay. So, that is the formula for the shear stress distribution in the cross section, and there will be a point in the plane of the cross section about which, when we measure the torque due to this shear stress distribution, then it will be 0, and that point is called the shear center. Okay. So, shear center by definition so this is a point in the plane of the cross section relative to which the net torque due to shear stress distribution and this again because of the applied transverse load. So, this is a point relative to which the net torque due to shear stress distribution vanishes. Okay. So, it is 0. So, suppose that that point in this plane of the cross section is somewhere over here, and let us denote it by S C for shear center, and then the centroid would be at somewhere at point O, okay, and we have the axis y and z in the plane of the cross section. So, that is your y axis and z axis, and let us suppose the shear center has got coordinate delta y and delta z in this coordinate system. Okay. And then our goal is to find out the two values delta y and delta z, the location of the shear center, so that the torque due to the shear stress distribution vanishes. So, to find this, we have to simply write down the formula for torque due to shear stress distribution. Recall that torque is the moment along the axis of the beam, that means in the x direction. So, what we can do is simply find out the moment about the shear center and then dot it with I, that will give me torque. Okay. So, let us say I denote torque by T. So, torque about the shear center, that is moment about the shear center and dotted with unit vector I, is not it. Now, what is the moment about the shear center? So, in this cross section, suppose any point we denote by P. So, this vector is position vector of P relative to the shear center, correct. So, the moment due to shear stress distribution, that is going to be the integration over the cross section, then the arm position vector of the point P relative to the shear center, cross product the shear stress tau x s, and that is acting in the direction s hat. Remember, s hat is the direction along the periphery of the cross section, is not it. So, this and we dot with unit vector I to get torque, okay, dA. So, this is the torque about the shear center, and we have to say that it is equal to 0, all right. Now, R P of S C, so position vector of the point P relative to shear center, which is an unknown, could also be written as position vector of the point P relative to the centroid, is not it, the point O here. So, basically we have two more vectors and we can use triangle law of addition. So, on the right hand side we then have R P relative to O plus R O relative to shear center, correct. So, this thing over here is minus of delta y of j plus delta z of k, is not it, because R O relative to S C is nothing but negative of R S C relative to O, all right. So, we can substitute this definition in this integral and we get integration over the omega of R P relative to O cross product tau x s s and dot with I dA plus the second integral, integration over omega, and we have a minus sign here of delta y j plus delta z k cross product tau x s s hat, right, dot I dA. Okay. Let us focus on the second integral, which can be simplified. Notice that delta y and delta z, the location of the shear center, is a unique quantity. So, it can be taken out of the integral, is not it? So, this thing here becomes minus delta y of j plus delta z of k cross product integration of the shear stress dA, and then you dot the whole thing with unit vector I. But look at this integral here, this is the integration of the shear stress over the entire cross section. So, that is nothing but what is the resultant shear force in the cross section, is not it. So, we can denote this integral by the vector v, which can in general have two components v y and v z. Okay. So, this is v y of j plus v z of k. All right. Now, if you further work this out, what do we get? So, we have j cross j, that is 0. So, basically this combination gives me 0. So, we have to look for cross combinations. So, j cross k is going to give me I, and then we dot with I, we get 1, and k cross j is going to give me minus I, which we when dot with I gives me minus 1. So, finally, this whole thing can be written as minus delta y v z minus delta z v y. Okay. All right. Now, let us focus on the first term. Now, because we said that our cross section is thin, so we can do some thin approximation. So, look at the first integral here. The cross section, which is a double integral, we can think of it as an integration over the S, right, the arc length S, and the integration over thickness T, and we have position vector of any point in the cross section relative to the centroid, cross product tau x s, right, and then we have S hat, and this has to be dotted with unit vector I dA, and dA then becomes ds into dt, is not it. Then we can recall that tau x s is independent of thickness, is not it. So, in this integral, what is really varying with thickness? It is the position vector of p relative to O, is not it. So, we can write this integral as integration over S, and then we have integration over the thickness T, position vector of p relative to O, okay, which is a function of both S and T, dt, all right. So, work out this integration and then do the cross product with the shear stress tau x s, because it is independent of thickness. So, it can be taken out of the thickness integral, okay, S hat ds, okay, and of course, finally, the whole thing has to be dotted with I. So, this whole thing gets dotted with I. Okay. So, what can we say about this quantity right here? So, it is the first moment while integrating through the thickness, is not it? So, we can simply replace this with position vector of a point P naught, which is at the central location on the thickness line, okay, relative to the centroid O, and this is then only a function of S times the thickness, is not it? So, where is that point P naught? So, we can come back to this figure and we can say that a point at the center of the thickness line. So, that is your P naught. So, find out the position vector of that point, which is R P naught. So, you can think of a green line running through the cross section, which is the center line, okay, and that is given by R P naught. All right. So, we can now come back here and then this becomes integration over the arc length S, which goes from 0 to let us say L. Do not confuse this L with the length of the beam, it is simply the arc length along the cross section. Okay. So, maybe I will write it as L C for length along the cross section, and then we have the thickness T which comes out of the integral, and we have R P naught relative to O, and that is a function of arc length cross product tau x s of S hat dotted with I d s. Okay. So, that was the first integral, and the second integral we have already seen that this is minus delta y v z minus delta z v y. All right. So, therefore, when we work out this integral, we will get some constant, let us say C y into v y plus C z into v z, okay, where C y and C z are integration over the arc length of the cross section. All right. And we have minus delta y v z minus delta z v y, and this has to be equal to 0. So, this means we have C y plus delta z times v y plus C z minus delta y times v z, and this has to be equal to 0, and this holds for any v y and v z. Okay. So, this finally implies that delta y is C z and delta z is C y. Okay. So, this is how we can obtain the location of the shear center delta y and delta z. All right. You can also think of getting the expression for C z and C y. So, think of a simpler situation where we only have v y acting, and that is also acting through the principal axis. All right. So, suppose only v y is present and y z axis are also the principal axis. All right. So, in that case I y z becomes 0, is not it, and we had found out that tau x s simplifies to the following expression minus v y which is a function of x times q y, and that is the function of s, all right, divided by I z z into the thickness T s, all right. So, can we now plug in this in the above expression and see what do we get for C y, for example. Okay. When we plug this formula for tau x s in this integral over here, we simply have T times integration over the arc length r of p naught relative to O cross product tau x s, which has got another minus. So, minus V y into q y over I z z times T s, right, and that is along s hat, and we then dot it with I d s, is not it. So, this becomes, we have V y into minus of thickness T and integration over the arc length S r p naught with respect to centroid cross product q y divided by T s, right, and I z z also comes out of the integral, because it is a unique number for the cross section s hat d s. Okay. And this expression right here within the bracket, so that is my C y. Okay. And we have seen that C y is equal to delta z. So, if you want to know the z coordinate of the shear center, you simply do this integral. Likewise, you can also find out an expression for the y coordinate of the shear center, delta y, all right. So, just to give a recap, shear center is the point about which the torque due to shear stress distribution vanishes. You know, it has another interesting property. Think of a beam with an unsymmetrical cross section. Okay. So, we have this beam whose cross section is unsymmetrical, and it is clamped on one end, all right. And so, on the free end we might be applying, let us say, a point load in the transverse direction. So, suppose that the centroid is somewhere here, which we denote by O, and then the shear center let us denote by a different color. Suppose it is somewhere over here, and that is S C. Okay. Likewise, for the S equal to 0 cross section, the left end cross section of the beam, it is also going to have its shear center somewhere over here, S C, and its centroid O, okay. And then we can join the 2 points to get the line of centroids of the entire cross sections. Similarly, we can join the 2 shear centers to get the line of shear centers. Okay. And suppose that we are applying a force which is, let us say, not passing through the shear center. Okay. maybe it is passing through a different point, let us say that point is A, and we are applying a force V over here, all right. Now, as the beam deforms, it will finally be in static equilibrium. So, that means net force and net moment on this beam should be equal to 0, right. So, let us suppose we isolate this beam from the clamped support, then the clamped support is going to exert some traction on that cross section over there, right, and we will have shear stress distribution in that cross section also, which will follow the formula that we just wrote down. Okay. And since it is an equilibrium, the net moment also should be 0, and in fact, net moment about any axis should also be 0. And suppose we find out moment about the axis of shear center or moment about the axis of centroid, all of them should be 0, is not it? Now, in this case, let us find out moment about the axis of shear center, which is actually torque, right, because the axis of shear center is along the direction I, which is the axis of the beam itself, all right. So, let us find out moment along the axis of shear center. Now, when you isolate this beam, what are the external loads that acts on this beam? So, on the right cross section you have this concentrated shear force V, and on the left cross section you have the distribution of shear stress due to the clamped support, is not it? But then we know that the torque due to that distribution about the shear center is 0, is not it? So, what is the total torque along the axis of shear center? So, to do that, let us just find out the torque about a point, okay, on the axis of shear center. So, let us say that is this point S C for the right cross section. So, we use the superscript R. So, torque about the shear center for the right cross section, that is nothing but torque about the shear center for the left cross section plus the position vector of the left cross section shear center relative to right cross section shear center, is not it, cross product with the shear force that is acting on the left cross section, right. But since the left cross section has got its normal along minus I, so shear force there is minus of V. Okay. So, that is minus of V, okay. And since we want to know the torque, we have to dot this with I, right, because we want to know the torque along the axis, but then this quantity here, that is also along the axis, right, this is along the axis. So, this thing as a whole vanishes. So, this was the torque due to left cross section, and then we find out torque for the right cross section where we have the force V acting. So, that is going to be equal to position vector of the point where we are applying the concentrated shear force V, which is the point A relative to the shear center of the right cross section, right. So, that is this line over here cross product the force, right, and we want that this should be 0. But you see this torque about the shear center of left cross section, this will also be 0, because by definition the torque about the shear center is 0. So, the first term here is 0, second term is also 0, but the third term, when can this be 0? This will be 0 only if A and SCR, the shear center of the right cross section, they are coinciding, or the shear force V is acting along the line such that the line of action is passing through the shear center. So, basically this thing will be 0 only if A is equal to shear center, or the shear force V, its line of action passes through shear center. So, that is really interesting. This tells us if we do not apply this concentrated shear force V passing through the shear center, then the net torque on this beam will not vanish, and then the beam will have a tendency to twist about its axis. Is not it interesting? Although you are applying a transverse shear force, but the beam is also trying to twist. So, in a way we have got bending and twisting coupling. Okay. But the bottom line is that if we do not want the beam to twist, we must apply the shear force passing through the shear center. If you do not do it, then the beam will simply twist. Okay. So, that is really interesting about shear center. So, how can we find such points? For example, look at a L shaped cross section. Suppose we have an L shaped cross section. Which is thin and open. So, if it is thin and open, then we know that shear stress simply flows from one end of the cross section to the other end. And in this case, what is the potential point about which the torque due to this shear stress distribution is going to vanish? So, we can see that this point right here is the point such that all these shear stresses are passing through this point. So, when we find out net torque about this point, then it will be 0. So, this is the shear center. Okay. Let us look at an annular cross section. In this case, it turns out the shear center is right at the center itself. Centroid and shear center are coincident, but this is not always the case. You see, this is also not an open cross section, it is a closed cross section. Let us, for example, think of a cross section like this. Okay. In this case, suppose that the shear is flowing in this way, then which is the potential point for the shear center? can the shear center, for example, lie in this green region here? You pick any point in this green region, and we will notice that the torque due to all these shear stresses, they are all in the same direction. So, it is never going to vanish. So, the shear center will never lie in this green region, it is actually going to lie out of this green region. It is somewhere on this side. Okay. You can also prove that shear center always lies on the line of symmetry of the cross section. So, if a cross section is symmetric about a line, then shear center is always going to lie on that particular line. For example, if we think of a cross section which has got the shape of a heart, okay. So, this has got a line of symmetry which is this vertical line, and shear center will be a point somewhere on this line only. Okay. So, shear center lies somewhere on this line, and the take home message basically is that shear center always lies on the line of symmetry of the cross section. Okay. You know, if you have a cross section which has got two lines of symmetry, then since shear center has to lie on both the lines, then the only point possible is the intersection of those two lines. Okay. For example, a cross section like this, it has got actually more than two lines of symmetry. One is this, then this is also a line of symmetry, then this actually also is a line of symmetry, and this is also a line of symmetry. And since the shear center has to lie on line of symmetry, then only possible point is the center itself here. So, in this case this becomes the shear center. Okay. Let us look at an even interesting case. Suppose we have a cross section which has the shape of an annulus, but it is cut. Okay, so, it is a cut cross section. So, in this case we do not have more than one line of symmetry, there is only one line of symmetry, which is this one. So, if you think of this green line right here, then this is not a line of symmetry, because we have only one cut, we do not have two cuts. So, if you reflect your cross section about the green line, you do not get the same cross section. Therefore, it is not a line of symmetry. So, it has only one line of symmetry. So, shear center does not get completely known, but all that we know is that it is going to lie on this black line. So, shear center lies on this black line. Okay. And since it is open and say it is also thin, then we know the shear stress is going to flow along the periphery of the cross section, okay. And again, can shear center lie within this circular region? Can it be, for example, in this green region? Can we have shear center within the cross section? It turns out no, because you take any point within the cross section, and when we find out torque due to this shear stress, they all contribute in the same direction. So, torque never vanishes. So, it has to lie outside this cross section, and it turns out it lies somewhere over here. So, you see it is not physically on the cross section. The shear center can also be outside the cross section, which we call as on an extension of the cross section. Okay, so, this is a very interesting case where the shear center does not lie on the cross section, but on an extension of it. So, if we have a beam with this cross section and I am applying a shear force and I want that the beam does not twist, then what should we do? We cannot apply the shear force on any point in the cross section, right. If we do that, then the torque balance is going to fail. So, in that case we have to have an extension of the cross section, right. So, let me just draw this beam. Which has got a cut. And if we clamp it on one side, then we have to actually have an extension of the cross section somewhere here. So, we have to maybe weld a small rod in the cross section somewhere here, and then apply the force at the shear center. So, V should be applied on the extension of the cross section. If we do that, only then this beam is not going to twist, otherwise it is also going to twist. So, it is very interesting, is not it? So, let us try to find out the exact location of shear center for this cross section. So, we are again going to draw the cross section. And we know that shear center has to lie on this dashed line. Suppose that the mean radius is big R and the thickness is T, and let us say the shear center lies at a distance of delta from the centroid. This is basically the shear center, and we are applying a force V y here, is not it? Then only it will not twist. Now, we know that the torque due to shear stress distribution has to vanish about the shear center, which let us say is the point A. So, let us try to find out the torque. So, we have to do an integration over the cross section. Let us suppose we go by arc length S and we look at this segment, and then we have shear stress here, and tau x s we figured out that is minus of shear force V y into q y. So, that is the first moment of the area from S equal to 0 up to the point S, which in this case is the first moment of this green shaded region. So, that is for q y, and this gets divided by I z z of the entire cross section multiplied by the thickness T, okay. And then the torque about the point A. So, that is the integration over the cross section, and we have position vector of any point in the cross section relative to point A cross product tau x s, which acts along the tangent to the cross section, which is S hat, and then we dot this with I and d A. So, that is the torque about the shear center, which has to be equal to 0, is not it? Okay. So, we can write this as integration over the cross section, and R P A becomes position vector of the point P relative to the centroid of the cross section, which say is O here, plus R O relative to A cross product tau x s of S hat, and then this whole thing has to be dotted with I, so that we indeed get the torque, and d A has to be equal to 0, right. Okay. Let us further work on it. Now, what is R P relative to O? So, P is a point here, right, P is a point over here. So, R P relative to O is simply a radial line, correct. So, that is your radius small r E r. So, that is R P O plus R O A. So, R O A, as you can see here, it is pointing in the negative z direction. So, here is your y axis, and then that is your z axis. So, R O A is negative z. So, we get minus delta times k cross product tau x s into S hat, and S hat in this case is along the periphery of the cross section, which is actually E theta, right. So, that is E theta, and then the whole thing we again dot with I dA. Okay. So, this means torque T about the shear center A, and here since delta is constant, it comes out of the integration and we have minus of delta k cross product integration over the cross section of tau x s E theta, and then we dot the whole thing with I. Okay. Then the second term we have plus integration over the cross section of R E R cross product tau x s E theta dot with I dA, but then E r cross E theta is simply E z, right, and I is pointing in the axial direction. So, this is basically R times tau x s dA, all right. Let us further come here. What is the first term here? You see the integration over here, we are integrating the shear stress over the entire cross section, that is simply going to give me the net shear force in the cross section, which in this case is V y. Okay. So, we get here minus delta k cross V y in the j direction, and then we dot it with I, all right. Now, what is this whole thing? So, k cross j is negative I dot with I, you get negative I. So, you have one more negative here. So, it is finally V y times delta plus the integration over the cross section R tau x s dA. Okay. Let us now use the thin tube approximation. If it is thin, then we know that tau x s does not vary through the thickness of the cross section. So, in that case the integration gets simplified. So, we could also write this as integration over omega r tau x s r dr d theta, right, and then the integral through the radius, since it is very thin, we simply get the thickness t. So, this gives me simply an integration over theta from 0 to 2 pi r square into thickness t tau x s d theta. All right. Let us now plug in the formula for tau x s. So, we have already seen that tau x s is minus V y into q y over I z z times the thickness t. Now, what is q y for the shaded region? So, let us have the shaded region here. So, it is an arc of the circle. And let us say this is theta. So, we can think of a strip here, thin strip, which makes an angle d theta. So, this is d theta, and for this thin strip, what is the y coordinate? So, this y coordinate is r times sin theta, and what is the area? The area is simply the thickness t into r d theta, is not it? Okay. So, what is then dqy, because we are only looking for the small area here, that is equal to y bar of this small area into dA, and that is equal to r sin theta times t times r d theta. Okay. So, what is then qy? It is simply the integration of dqy from 0 to theta, right. So, this becomes r square t integral sin theta d theta going from 0 to theta, okay, which becomes r square t into 1 minus cos theta. Okay. Now, we can plug in this qy in our formula for shear stress here, and further in this formula right here we finally get Vy into delta plus the integration from 0 to 2 pi r square t into tau xs, which is minus Vy into qy, which is again r square t into 1 minus cos theta divided by Izz times the thickness t, okay, and this has to be equal to 0. So, this further implies Vy into delta plus r to the power 4 into t square divided by Izz times the thickness t into minus Vy, and then integration 0 to 2 pi 1 minus cos theta d theta. Okay. So, when you work out the whole thing, it simply is Vy into triangle minus r to the power 4 into the thickness t into Vy divided by Izz into 2 pi. Okay. The integration simply gives us 2 pi. And what is Izz for a annular cross section? Let me redraw the cross section here. See, the cut is really thin. So, actually the whole annulus is actually complete and there is a very thin cut. So, as far as computing Ixx, Iyy and Izz is concerned, we can forget about this thin cut. Okay. So, about the centroid O, we have to get Izz. Now, since this is a circular cross section, Izz and Iyy will be same, and Ixx is actually Iyy plus Izz, which is 2 times Izz, and that is coming from perpendicular axis theorem, which you may have learnt in your first year mechanics course. Okay. So, Izz is then Ixx by 2, and what is Ixx? That is the polar moment of area, because x is the normal to this cross section. So, Ixx is simply polar moment of area. Okay. So, Ixx is then integration over the cross section r square dA, and again assuming that the cross section is really thin, your dA is r dr d theta, right. So, we get r cube dr d theta, and since it is very thin, it also becomes big R cube into T and then 0 to 2 pi d theta. So, it is finally 2 pi R cube into T, okay, and that means your I z z is pi times R cube into T. Okay. So, let us plug it in the formula over here, and this has to be equal to 0. So, this means V y into delta minus r to the power 4 into t into V y into 2 pi divided by I z z, that is pi r cube into t. So, we have lots of cancellations here, this pi cancels this pi, thickness cancels here, and r cube cancels this power here, and V y cancels this V y here, and this is equal to 0. So, that means your delta is finally equal to 2 r. Okay. So, that is how we get the position of the shear center, and you can see delta being 2 r, it indeed is out of this green region that we are talking about, is not it. So, here you have to go by 2 r to get to the shear center. So, when you go by r from the centroid, you get on the cross section, you have to go further r to get to the shear center. Okay. So, this delta basically here is 2 r, all right. So, I hope that you got some idea about shear center in this class. So, with this we finished the lecture on bending of beams. So, we started with pure bending, then we did non-uniform bending, then we did bending of unsymmetrical beams, and finally, we figured out when you apply shear force to an unsymmetrical beam, it can also twist, but then if you want to stop that twist, you have to apply the shear force passing through a special point, that is the shear center of the cross section. Only then the beam does not twist, and then it is simply going to bend. Okay. So, with this I will end this lecture, and in the next lecture we are going to talk about beam theory. All right. Thank you.